Hello. Hi guys, good morning. Welcome back to new video. Ki hal chal? I hope you guys are doing good. In this, we're gonna see problem number 4 of today's contest. Although it is marked as hard, actually it is also hard. Just not because of what is applied here, just because of the complex problem statement and to actually infer a very simplified approach from it. Cool, let's see. But before that, if again, just a big disclaimer, if you don't know or you haven't watched this video about digit DP, then please go and watch it because that's going to be used here. And again, how to do it, all the intuitions that I have told about digit DP in this video. Cool. Let's start off. It simply says that you are given a binary string S. You know binary string? Made of zeros and ones, which actually represents a number. Now, before even going forward, the first thing which could come to your mind is Aryan, I will convert that binary string to a number itself. But the binary string length itself is 800. If the length of the binary string would have been less than equal to 64, you could have converted that to a long at max. Again, I am talking about the normal languages. Java, C++. Even in a Python, you will get TLE if you just try to convert this much big number and try to iterate on it. So ultimately, with this fact that the length of the binary string is less than equal to 800, you realize that you cannot obviously convert this string to number directly. That's not possible because that number will be very large. Now, let's see further. Again, this is a very big hint of what can be used. Just one line, first line gave a very big hint. Now, next says that I'm also given an integer k. As you can see, I'm given an integer k also. What that integer k means? That integer simply says that an integer x is called K-reducible if performing the following operation at most k times reduces it to 1. This is itself one of the most critical and most complicated statement in the entire problem. I'll explain you why. Again, if you understand it, it will take minutes for you and to get the actual solution also. It simply says that if your number, given number x, again, x imagine it as n as a number is given to you as 6. It's binary, again, forget about it, what k is and what reducible is. X as 6, its binary representation is 110. Number of set bits in its binary representation are 2. So I will take one operation to convert 6 to 2. Makes sense? And how did I convert? I got the set bits and this conversion from number to its corresponding set bits value is one operation. Same way, if my x is 2 now, number of set bits in it is 1. So converting 2 to 1 is one operation. Thus, I was able to get 6 to 1 in total of 2 operations, and allowed operations were also at most 2. This is what this statement means, that an integer x is k-reducible, which means I can reduce that x to 1 in k steps, in which each step is defined as replacing the number x with the count of set bits in its binary representation. Okay, ultimately they have given the same example here itself. Now you have to return an integer denoting the number of a positive integer less than n. This should trigger something. I'm not saying AK-47, but it should at least trigger that you have to find positive integers less than n. And also in this case, you cannot convert your n to an integer. You have to keep it as a string itself, and that string here in this case is a binary string. So when you have to get some numbers less than some number, which is n in this case, and also keeping the fact that you cannot convert it to an actual integer and you have to get the number less while iterating on a string, that is where you should know that you have to use a digit DP, because digit DP have a constraint called as tight, which helps you to get a number which is less or maybe less than equal to. This tight constraint in digit DP helps us to iterate on the string, iterate as an index of the string. Tight maintains that the number will remain less, and obviously these two are used for simple iteration, but obviously we know that we have our maqsad. That maqsad is the condition. What we have to find? We have to find the number of such numbers following the condition. Condition is K reducible. Now you know that you will apply digit DP here, right? That's one thing you know, and also you know that what is your maqsad. What is maqsad in condition? Condition is K reducible. So let's quickly jump out to example, and then we will go on to that again. Firstly, you should understand example, and I'm highly there's a high possibility that for many of you, you will be confused in the example itself. So it says my S is 111. Although for simplicity, I have converted this number to a 7. I cannot do it, but still I converted it to a number 7, right? Just for explanation. Then I actually ended up getting all the candidates which are less than 7. Now, getting all these candidates, who will do this job for us? This job will be done by digit DP for us. Then I will see that, okay, how many steps are required for these candidates, and whosoever is K reducible, I will add a +1 for it. So as you can see, I am my maximum allowed steps are actually 1. But here steps required are 2. So these will not be counted. Answer will be these 3, which is 1, 2 and 4. As you can see, 1, 2 and 4. But now you might ask, Aryan, how did you calculate these steps? Obviously, this I showed you here itself, that 6 needs 2 steps to reduce to 1. Same way, if I just take the sub problem of it, you will see that 2 needs 1 step to reduce to 1. And obviously 1 is already there, so it will not need any step at all. Now you might also, same way, the way I made it here, the same way you can also derive for these values. But the fact here is, many people might get confused. Aryan, it seems like 1 has, okay, 1 is, let's say, some exception, but 2 has 1 bit, it requires 1 step. 3 has 2 bits, it requires 2 steps. 4 has 1 bit, it requires 1 step. 5 has 2 bit, it required 2 steps. 6 has 2 bit, it required 2 steps. Aryan, is it the fact that I am actually saying the bit count is also equal to the count of steps required to reach 1? Again, this count of steps required to reach 1 is actually this steps itself. Is it true? It's a coincidence that it is happening here. It is not true, because this is not the problem statement. What was happening? Problem statement mentioned that if you have a number, let's take x equal 31, it has 5 set bits. By your assumption, answer should have been 5, but no, because if it has 5 set bits, value of set bits is 5. In one operation, it will become 31 will become 5. In another operation, this 5 will become 2, because 5 has 2 set bits. In other operation, it will become 1, because 2 has just 1 set bit. So in total, for 31 to reach to 1, it will need 3 steps, 1, 2 and 3. Did you see a very basic DP applied? Again, I'm not saying the actual digit DP, I'm saying a very basic DP. Did you see that? That is simply, if you know the answer for 2 set bits, you can easily compute the answer for 5 set bits by just adding a +1. For me, again, let's say the abbreviation of this entire term, count of steps required to reach 1. Let's say the abbreviation is count, CNT. Remember this, I will use the same thing in future. So for this count of 1, okay, like let's start from here. Let's say this is, you have to reach. So for 2, you had 1 set bit here. So I will say for 1 set bit, if I have 1 set bit, again, this 1 is representing count of a set bit. Remember that fact. So it will say, okay, the value is 1. Now I will say, what is for this? I have 2 set bits. For 2 set bits, it will be 1 plus, obviously, the value which I had, or I should say the actual set bit count, 2. So I'll say count of 1. Again, this is actually confusing part. So hold on with me. I'll explain it very carefully. This is the actual confusing part, because getting the count of set bits, actual set bits, people get confused in this one only. Now, obviously, I will use this fact that the count of 5, which means count of steps required to reach 1 with 5 set bits will be one more step. And ultimately I know that because considering count, if I have 5 set bits, which can be any number, it can be a 1 0 1 1 0 1 1 also, count is still 5. So he just say the actual value will be 1 because one step will be used. As you can see, one step was used, but one step to reach where? To reach a value which is 5, whose count of set bits will be 2. Did you see that fact? That is the exact thing, which again, this is simply a DP. You are using a sub problem's value to compute your value. So what we realized here is that ultimately here 3 steps were required. We tried to build a corresponding relation and use a corresponding sub problem. This is a very basic portion of DP here applied, that for any count, again remember this count is an abbreviation for count of steps to reach 1. This will be 5. 5 is actually the bit count I have for a number 31. Bit count is 5, right? Now Aryan, but then how would you know that at max what should be the bit count, as in at what point are you about to reach, or what's your plan to reach at what point? We will see that. But still, if this is a bit count, I realize that one step will be required, but to reach where? Obviously, if I had 5 bit which are set, it will say that my value is 5, and ultimately 5 as a value will have 2 bits. So ultimately I am saying same thing count, but now the number of set bits in this value which I have. And this is actually the relation to get you the count of steps to reach 1 for any number of set bits. Cool. So we will use this relation. Now you might say, Aryan, okay, it makes sense that I will start by saying that the number of set bits count is 1. And for that 1 as the count, the operation or the steps required will also be 1. For any case, if you take 2, if you take 4, if you take 8, if you take 16, any one of them, the count, again, for every one of them, these are, let's say, the x values. But actually, I pass in here the number of set bits. So obviously, the operation required will be 1. Because in one operation, I can make all of them to 1. All of them to 1. Cool. Now, the fact is, up till what point I should go, which means that, okay, this count can start from, let's say, 1, or maybe you can say count will start from 2. Here, remember, 2 represents number of set bits. Up till what point I should go? I should make it go. Obviously, the max number of a set bits count. I remembered my problem says that I have 800 length of binary string, which means that the number x itself can be at max 2 raised to power 800, which ultimately says I can have 800 set bits. If I can have 800 set bits at max bit count, which can be, it can be 800. Thus, I will simply use the simple linear DP approach to start. Again, firstly, I said that for the number of set bits as 1, the operation or the count required for it to reach a value of 1 is just one step. This is my, let's say, base case. Then I simply start iterating and say that I will go on up till my bit count of 800, because I know this is the maximum bit count which I could have. Then I will have the same recurrence relation which I saw here, that count of the input which I had, bit count, it will be 1 plus same count of bit counts, actual bit count 5, number of a set bit in 5. So this is, as you can see, this line exactly, and this says number of a set bit in the bit count. So if I replace this with 5, this with 5, so number of a set bit in 5 will be 2. So this value will be 2. Here I will put a 2, and here I will put a value 5. So to derive the count of 5, I will say 1 plus count of 2. And I know count of 2 actually says 2 set bits. Cool. And this is how I can simply go and derive, or I can say pre-compute my count. Now, I have done the most critical portion of this problem, which is deriving this. And again, I say this is the most critical because this is very confusing. Now comes the easy part, which is applying digit DP. Because obviously we know that we have to apply digit DP, but apply digit DP as in for what? That's a question. Good question. So if you remember our maqsad, as I always say, maqsad nahi bhulna hai. Your prime aim was number of a positive integer less than equal, less than, not equal, less than n, whose count of set bit, again remember count was abbreviation of count of steps to reach 1, should be less than equal to k, because I am allowed at most k steps. So this was the maqsad. Let's break this maqsad down. Number of a positive integer. Obviously, my DP will store my maqsad. So my DP will store my number of positive such integers. But I have to get less than the required n. Now n I am actually computing by using my string, binary string as an array. So I have to use my string. Obviously, I will iterate on it. So I will also use the corresponding index. Now I know I have to compute that less than logic. For less than logic, I know I will apply digit DP. For the prime aim of a digit DP, it actually needs tight. If you don't know what tight is, why it is used, go and watch that video which I mentioned above. Although you might get it here also, because I have dry run the exact stuff. And also the condition was this condition, that count of set bits should be less than equal to k. Count I have already computed, pre-computed, but for that I need to pass in something. That something will be set bits. So number of set bits I will have to pass in my argument. So this is corresponding my solve function. Obviously it's a recursive. We will write simple recursive. For a recursive, we will obviously start off by saying, okay, I will give you the string, start off with the index 0. Obviously in the very beginning everything is tight. For the folks who don't know what tight means that, okay, go watch that video. But tight means that if I have number 843, I want to get numbers less than 843. So if I am here, I say the tight as 1. I cannot go beyond 8. But if at this place I place, if at this place, which means this index, I place a number 7, now I will pass in tight as 0, which means now the next number is not tight, which means now I can place a number higher than 4 also. But if I place at 8 only here, then I will have to propagate tight as 1, which will ultimately mean that I cannot place any number more than 4. So this is how tight as a variable help us, that can you place a number higher than it or not. If you want proper diagram, go and watch that video. Now this indicates the initial number of set bit count. Now for simple case, base case would be nothing but as you reach on to the end index. Right now, as you reach on to the end index, remember your maqsad. You said that it should be less than n. Now tight, if the tight is 1, so ultimately if the tight is 1, which means that you exactly were propagating tight as 1, which means you are exactly propagating 843 previously. So if tight in the very end is 1, which means that you are actually, your previous number, which is whatsoever you were making, that exactly is n, but you wanted less than n. So if the tight is 1 in the very end, which means that your previous number, like the number, or I should say the index which you actually left, just n minus 1, the number which you built previously was actually exactly equal to n, which you don't want. So simply return a 0, because you want number less than n. Less than n. Or else there's one condition, simple condition, if the set bit count is 0, which means that there's no set bits itself. Obviously my maqsad was to reach 1. If the set bits itself 0, which means that value is 0, from 0 I cannot reach 1. So that's simply written as 0 also. But elsewise I'm good. But still there's one more condition, that the count of a set bits should be less than equal to k. So I'll just put this condition, that count of set bits should be less than equal to k. Now simple memorization, as you simply know that we are having I, index, tight, and also my set bits. Remember, I is iterating on the string which is of length 800. Tight is either true or false, which means 0 or 1. Set bits is at max. We remember the number of set bits can be 800. Now the actual recursive case, what it will be, let's see the try run. So imagining, again I took a random string s. initially in the very beginning, I will put the constraint as tight. Yes, it should be. In the very beginning, the set bit count is 0. I am at I. I have to start traversing my I. Considering I am at I have my variable as tight. Okay, let's see what will happen. What I will do, the value was 1. Either I can make it a 1 only, I can make it a 0. If I make it a 0, obviously my tight bound will no more remain because I reduce the value. Now I am free to put any value whatsoever in future. So my tight bound, it became a 0. Once a tight becomes 0, it remains 0. That's it. It will never become as 1. But if the tight is 1, I have to make sure I have to propagate that tight because next value should also be taken care of. Now, this indicates that I have placed this corresponding value. Now, obviously, then as I placed a 1 here, then number of set bit count increased by 1. Okay, at this position, again, I will have the corresponding two options, always two options. You will see that either you can place a 1 here or you can place a 0 here. If you place a 0 here, again, your tight bound got to 0. No more, it is no more tight. And the set bit count also remained 1 because this value you put as 0. But if you put as 1, the set bit count will become 2, but the tight will still remain a 1 because obviously you are actually not on a tight bound. Now the value is 0. Again, do you think you have two options? Obviously not, because you were tight. If I am tight, I showed you previously, I cannot increase the value if I am tight. If I cannot increase the value if I am tight, which means I can never place a 1. I can only place a 0. That's the only option I have. And with that option, I will still remain tight. My still set bit count will still remain 2, and I will move forward. Right? Same way here, it was not tight. It was not tight. So I can place either a 1 here or a 0 here. That's the option with me. That is the benefit, that you are able to get all the numbers less than n. And obviously here you place a 1, so the count of a set bit increased by 1. Here you place a 0, so count remained as it is. And you will see the same way the entire recursion tree will actually build. Okay, I'll show you like this, small. Now, if I show you the code, exactly same code. Now, if the tight is 1, as I showed you, if the character is 0, you only and only have one option, move to next index. Tight will still remain 1. Again, this tight, if it's 1, obviously it will be 1 only. And the set bit count also will remain as is. As you can see, as the value was 0, tight was 1. You remembered that this will still remain 0, tight will still remain 1, the set bit count will still remain as is. Elsewise, the tight is 1, then obviously you have two options. If the value is 1, as I saw in the very beginning case, that if the tight is 1, if it is 1, I have two options. Either I can place a 1 or I can place a 0. If I place a 1, my tight will become 1. Oh, sorry, it will remain 1, and the set bit count will increase by 1. My tight will become 0. Set bit count will remain as is. Cool. So let's see that it will be S. Again, this indicates that I am placing a 1. As you can see, the set bit count increased by 1. Tight will remain tight. And here you will see, if I placed a 0, the set bit count will remain as is. Tight will become non-tight. I have to place, purposely I will have to place 0 here, and I will move on to next index. Okay, so this was the fact when the things were tight. I know you like tight. Jeans. Hold on, jeans. Cool. Now, elsewise, what will happen? What if the value is not tight? If it is not tight, you are chill. You are complete chill, which means place a 1 or a 0, totally up to you. So what I'll do? I will simply say again, once the things are not tight, they will always be not tight. Remember that fact. So again, this, when I say tight here, it actually means 0, 0 itself. So once the things are not tight, they will always remain non-tight, right? Then if I place a 1, bit count will increase by 1. If I place a 0, it will not increase. But still, I will have to move to next index. This is the only recursive case which you have to do. Exactly same. Again, this is the easier part. The tricky part was this one, which I showed you above. This one. Cool. Now let's do a summary of the code itself. So in the very beginning, I simply build my corresponding DP array with filling with -1. Then I actually did this pre-processing of count of steps to reach 1. Again, remember, in the argument, I am passing the bit count and not the value, right? Then I call my recursive function by saying string is s, index is 0, tight is still in the very beginning, and the set count or set bit count is 0. Then the exact same piece of recursive code. Base case, as I mentioned, memoization, as I mentioned, recursive case, as I mentioned, and ultimately returning with the memoized value. And thus, as you can simply see, I'm iterating, or I'm trying for all the possibilities of I, tight, and set bits. I is 800, which is n. My tight is 2, and my set bits is also 800, which is n. So complexity will be O of n square into 2. Space also will be O of n square into 2. And that's your corresponding answer. Cool. I hope you guys got it. If yes, then do smash the like, baby. If you have not followed Twitter, please go and follow it, because we are more active on it rather than LinkedIn. Again, you can also join Discord and Telegram. That's also very, very, very active. Bye.